In this video, I'm going to look at the solutions for questions 39 to 41 found on page 191. This is at the very end of chapter 5. They talk about ozone and how the ozone hole developed. And this is an equation, a process that we'll get into much more when we get into organic chemistry. But basically, what you need to know from that section is that oxygen, O2, which is helpful to us, good thing, we breathe it, just double bonds with itself, whereas ozone is O3, so it double bonds and single bonds to itself. So the double bond in O2 is actually shorter and stronger because it's a true double bond, but in O3, it's really more like a 1.5 bond because it resonates between the two positions. So in question 39, they says concentration, there's the reactions. A, identify the step which is exothermic. Well, if you look at this, O2 to O, that's bond breaking, and bond breaking is always endothermic. Number 2, O2 plus O, that's bond making, and bond making, I just did that wrong. Yeah, bond making is exothermic. Bond breaking, endothermic, bond making is exothermic. And the third one, I'm also bond breaking, so bond breaking will be endothermic. So the only exothermic step is in number 2, where you're making bonds instead of breaking bonds. And then B wants to know what's the most endothermic step between 1 and 3. So what they're really asking is which one requires more energy or which one has the stronger bond. And as I just discussed, O2 is a stronger bond because it's a true double bond versus O3, which is a resonating double bond or a 1.5 bond. Number 40 wants to know, it says, using the data booklet, calculate the minimum wavelength of radiation needed to break the oxygen double bond in O3. And this one is very similar to the one they did on page 190, where they did it for O2. So this isn't really an important question to what we're going to be doing this year. They're just making the point, they're proving mathematically that the O2 bond is stronger in oxygen than it is in O3 ozone. So what we know is that it's delta H for a O2 bond in O3 has been calculated to be 468 kilojoules per mole. So if you're breaking a mole's worth of double O bonds, that means you need a mole's worth of photons. So I could really change this. 1 mole of photons would be 6.02 times 10 to the 23rd photons. So when I divide that, we're really talking 8.27 times 10 to the minus 22nd kilojoules per photon, or I'm going to go ahead and change that to 10 to the 19th joules per photon is what I need. Okay, so that's the energy I need. So to change that to a wavelength, and if you already compare this to number 40, when they did that same process, the energy needed by O2 was greater than this. So 8.27 times 10 to the minus 19th joules per photon. Now I can go ahead and convert that to a wavelength because you might remember this from last year. Planck's law says energy equals Planck's constant times the speed of light over wavelength, or I could rearrange that to wavelength equals hc over E. H is a given. It's 6.63463 times 10 to the minus 34. And speed of light is a constant, 3.0 times 10 to the 8th. This is joule seconds. This is meters per second. So my seconds have already canceled out. And I'm going to divide by the joules that I calculated above, 8.27 times 10 to the minus 19th joules per photon. And when this is all said and done, I end up with 2.41 times 10 to the minus 7th meters, or I can multiply that by 10 to the 9th, and that would be the same as 241 nanometers, because my joules cancel out, and it's 241 nanometers per photon is the minimum wavelength, which is a shorter wavelength than the 330 needed to break it in O2. And 41 says ozone decomposes with a longer wavelength than oxygen gas. Why? And actually, this is actually the O2 bond in oxygen, not ozone. I've got that miswritten up there. So this is O2 is 241, whereas O3 was the longer bond, the longer wavelength at 330, letting us know that for 41, why can it have a longer wavelength than oxygen gas? Because longer wavelength equates to less energy, which equates to a weaker bond, which we know is true because of the resonance. So all three questions just really drilling home the point that an O2 bond resonating with the single bond is longer and weaker than an O2 bond that doesn't resonate.